So today we'll discuss random forest models. This is still a kind of a multivariate regression or classification type issue. So we're continuing the multiple variable theme. But for those that are familiar with the process of random forest, it's based on this idea of recursive partitioning or regression trees. So recursive partitioning is when we're using them, random forest that is, in a classification scheme where we might have multiple variables measured, and we're trying to predict, in the case of today's example, a species based on morphological traits. In my own research, we use this to try and predict species occurrence and distribution based on riverscape attributes that are distributed across space. But you may be interested in trying to make predictions about a continuous response variable, abundance of an organism, for example, in which case you can still use random forest models, but there it's in a regressive approach, a regression tree. But unlike a regression tree, and I'm going to show you what a recursive partitioning, just a very basic classification tree, and then we're going to contrast that with random forest, because in random forest, rather than creating a single tree, many trees are constructed with random subsets of the data. So the basic flow of operations is you take your data set, and these are typically data-hungry models. You need a lot of data. So for example, today we'll have 150 observations. Can't run it on limited data sets or unless you have a really strong pattern, but even then it doesn't perform well with small sample size. And that's because one of the first steps that it does is it takes your data set and it randomly draws observations with replacement. So it'll draw an observation and throw it back into the mix, and it'll randomly draw another observation. And it's going to keep those observations that are drawn in a data set or in a bag. And so that's a bootstrapped data set is what we call that. Random subsets of our data set with replication. We create this bag of data that are used to create a random forest model. And from that bag of data, instead of using all of the variables in the tree, I'm going to show you in a classification tree, random forest will select a subset of variables to try at each split in the tree. And it'll do that randomly. So it's creating these trees that are created with random subsets of the data using random variables. It does it multiple times. And so you can imagine why it might be called random forest. It's multiple trees, this is the term forest, and then they're created from random subsets of the data, so random forest. And then once the multiple trees are created, it goes through this concept of what some call voting, or thinking about the majority classifications across all of those hundreds of trees that are made. And this is a way of boosting our inference or including uncertainty in a classification tree. And the main idea is that many poor learners can collectively be a good learner. So taking all of these votes across the hundreds of trees, looking at the emergent kind of pattern in the data and using that for classification. You may hear it referred to as an ensemble approach. There's multiple lines of evidence being used collectively. And one of the benefits of this is we can think about things like evaluation of variable importance. So when you're using multiple predictor variables, it might be interesting to know which of those explains the most variation or might be most important for proper or correct classification. Okay, so that's a very short overview of random forests. I know there's a lot of help on these online nowadays. This is kind of what I'm doing today is geared towards those that recognize that you want to fit a random forest, you kind of understand some of those basics, and how do you do it in R? Okay, so we'll use 3 packages. We're going to use the rpart package to do a regressive partitioning. This is just to fit a single classification tree, so we can load that library. We're going to use the random forest, and notice it's camel caps, that F is capitalized. So we're going to load that package. And then there's another package, RF utilities, that follows the same camel cap there. And this is a useful package for thinking about model performance and evaluation. Particularly for today, we're going to use the package RF utilities to look at what's referred to as partial dependence plots, and then to do a cross-validation of our model, where we're subsetting the data, training models, and then considering how well those subsets predicts other subsets of the data. Okay, so more on that in a moment, but that's what we call cross-validation. So we'll load the RF utilities, okay? And we're going to be using the iris data. So these are data that are automatically loaded in R. This is not something that you have to download. If you just do data iris, you should be able to pull these. And we have looked at these before. If you'll remember in the lecture on non-metric multidimensional scaling in MDS, we used the iris data set. But just as a reminder, if we look at the names, we have measurements on iris. These are plants. So we're looking at sepal length, sepal width, petal length, and petal width. So those are continuous measurements of the morphology of these plants. And then there's a categorical variable that's species. And there's 3 different species in this data set, okay? And if I just bring this over and we consider our environment for just a moment, so many Zoom windows open here. 150 observations of 5 variables, okay? And that's 50 observations per per species for the 3 species. That's how we arrive at 150, okay? So pretty large sample size, and that's what we need for fitting these fitting these trees, okay? So the first thing that we're going to do is use a single recursive partitioning or classification tree. This is a methodology that will probably make sense after I plot it here in a minute, but it uses the data, all of the data, and it considers how can we categorize each of these species based on these measures of morphology, okay? So it's our part is the function that we're using. We're creating an object called tree. Our response variable is species. That's the 5th column from the iris data set. Use this little tilde to suggest species as a function of, and then this period, if you'll remember that period represents basically every other variable or every other column in the data set beyond species. So this is a shorthand way of writing out all 4 of these predictor variables, okay? You could do sepal.length plus sepal.width plus petal.length and plus petal.width in place of this, but that's a shorthand way of doing it, okay? The method we're going to be using is classification. Remember, if we had a continuous response variable measured on a scale, we could do a regressive tree, but we're going to classify here. And then there's just a couple of things under this control. So our partition control. This is the complexity parameter. This is going to help us to determine, as we grow out a tree and put more and more splits in there, typically we only want to add splits in the tree, or we only want to grow out a tree if those new splits explain some new variation in the data set, okay? So I have this set to 0 right now, but we're going to iteratively change that so you can kind of understand the difference between growing out a tree or pruning it back, okay? And then min split is just the minimum number of observations that have to be present for a split to occur. And if you're dealing with a really big data set, you might want to have, you know, multiple observations at each end of the branches of the tree. We call those nodes, okay? I'm going to plot this in a minute and we'll go over all this again. But min split equals 1 is the other thing that we could change. Okay, and then the last, I just put the comma and hit enter to go to the next line. The data are coming from iris, okay? So we can run this thing. We get in our environment an object called tree that's a list of 14. So it's a pretty complex output. We won't spend a lot of time going into the output, but I want to show you the plot, okay? Because I think illustrating that might be helpful. So the first thing I'm going to do is just partition this plotting window here using the par function. And then mf row is going to be 1 row by 1 row, and xpd equals na. The reason I'm doing that is to force that figure to plot in this plotting window down here, okay? Instead of it popping up in a new window or part of the text being cut off, okay? So I'm just gonna run that. It's gonna affect everything that's put into that plotting window now. We're gonna plot the tree. Try it one more time. Let's plot the tree, okay? And then we're gonna use text to add text to this object from this object called tree. And then we're going to do this use.in equals true to show the number of observations for each of those 3 species as they're split, okay? And then I'm going to zoom in on this, and hopefully everyone can see this zoomed in version, okay? So this is a classification tree. It's just a single tree. You're not moving into the realm of forest yet, but the whole idea here is to take your predictor variables, so petal.length, for example, and identify thresholds that might be useful for classifying the 3 species. And 3 species are Setosa, versicolor, or virginica. Okay, so what this shows here is petal length less than 2.45. If the petal length is less than 2.45, you go down this node, and it perfectly classifies all 50 of the Setosa. So it's 50 Setosa were put into this group, 0 of the versicolor, and 0 of the virginica. If petal length is greater than 2.45, then you go down this direction. Notice now we're adding another level into the tree here. So we're growing out that branch. Now we're thinking about petal width. If petal width is less than 1.75, you go down this direction. Then we're looking at petal length again. Notice we're using the same predictor variable twice there. Here, if petal length is less than 4.95, you go this direction, and then we're looking at petal width again. And if it's less than 1.65, it classifies 47 of the 50 versicolor. And then if you go all the way back up to here to petal width, if that's greater than 1.75, you go down this direction. And if the petal length is greater than 4.85, that's where 43 of the 50 virginica were classified, okay? So we're just going through the predictor variables. We're identifying thresholds so that we can classify each of these observations into a species, okay? This is a classification tree if you've never used one before, okay? And the R-part function that we used there went through and used all of the data to find the best split first. It's a hierarchical approach. It finds the best splitter. Then it goes within that, finds the next best splitter. It searches through all of the data. So we have 4 variables that we're using to predict this. Then it does the next split. That's what's happening here. Then it searches through all of the data again and does a split, and so on and so forth until we get down to some level where we have nodes. And that's what each of these places that has a label on here, we call those nodes on the tree, okay? Or the end of the branch. Okay, so yeah, of course.
So looking at that chart or that tree, I guess,
Yes,
like, so you know how on the bottom it has like the number of species per cat or each species? Is it possible that there will be multiple species at the end of a node, or does it have to keep splitting eventually? Like, does it have to split so that no 2 species are ever in the same ending up zone or node?
Yeah, let me show you the pruned version of the tree, and that might make more sense. Okay, so we went all the way down, and that's a very good observation, to where it's just 1 species in each of these nodes. But let's have a look if we go in and modify the code right here, the CP. So what we're when we set that equal to 0, essentially what that means is every time a new split is put in there, we'll retain the split regardless of the increase in variation that's explained. But we might say, well, we don't want to put a new split in the tree unless there's like 0.01% of variation is explained. And this is a way of reducing complexity of the tree. And so if we run it again with that, and then plot this, notice that the tree is less complex now. And we can add the text on there and to, not export, let me zoom. And then to answer your question, notice now that there's classification in Virginica here of 2 that we know to be versicolor, right? Because the first number, it's in alphabetical, or it's in order from alphabetical order. So Setosa is always the first group. So there's none that we know to be Setosa that are classified here, but there's 2 that we know to be versicolor that are classified there as Virginica. And then there's 4 that we know to be Virginica that are classified as Virginica. Okay. So I showed you the fully grown out tree where every node is resolved, but that's overly complex. And so we're pruning the tree back now to only include splits that increase to some extent the variation that's explained by the tree, okay? In terms of what we'll refer to later as node purity. So this node is pure. It got all of the Setosa and nothing else. But later on, we're going to think about how does that change if we change randomly the predictor variables that are tried at that split, okay? Very good question. Thanks, Alex. Okay, everyone else doing okay? You get the idea of just partitioning out the observations using this classification tree. And here, all of the data are used. And you could make some conclusions that petal length is important because it's used here. It's used a second time here. But there's a way of getting at uncertainty in this tree, and that's random forest, okay? And the idea is that, as I said, we're going to create a bootstrap data set. It's a subset of our total data set that's sampled with replacement. And then from that subset, we're going to create trees where we might try, instead of all of the variables at this first split, we may only try 2 of them, randomly selected, those 2. And then it picks the best classifier from those 2. Then it goes to the next split, and it subsamples only 2 at random. And between those 2, it assigns the best classifier. And we grow out that tree. And we start over. We do it again with randomly selected variables here and randomly selected variables here, and so on and so forth. And so you grow out these trees that are not identical because they're random subsets of the data, okay? And then by looking across all of those trees, kind of seeing the entire forest, we can look at emergent patterns from that, okay? So we'll just take that basic tree, and now we're going to extend that into the realm of random forest, okay? So that's what this next bit of code here is. And I'm introducing an idea here of a set seed. And so because we are randomly drawing data, if you were to do that again and again and again, you get random subsets of the data every time you did it. And every time you ran the random forest model, you would get a slightly different answer. If your data are really sloppy and it's not a great model, you might get wildly different answers across each of those iterations. But to facilitate returning the same predictions every time, we can use this set seed, where it's set.seed, and then parenthetically, you just put a random number in there. And that's going to set the starting point for the randomization that happens in the random forest, okay? So if you do set seed, I just chose 187 there. If you run that before line 31, you will always get the same output from line 31, okay? If you don't run set seed and you just ran line 31 again and again and again, you would get slightly different responses because there's different data being drawn. We're not, without using set seed, we're not controlling for where that randomization begins, okay? Now, with that said, if you all use 187, you still might get slightly different results from what I have, but it should be consistent every time, okay? And we can make some comparisons there if you want. So we're going to do set seed, and we just have to run that before you run the random forest every time, okay? So we're going to call this rf.mod. We're going to use the random forest function. It's the same name as the package, random forest with a capital F. We just tell it the response, in this case, species. That's our classes or categories that we want to try and predict. Notice we're using the same equation where it's as a function of all of the other variables in the iris data set. The number of trees we're going to grow out is 500, and the number of variables that we're going to randomly try at each split is 4, okay? You can run the default without in tree, which I think the default is 500. Remember, you can do !random forest, and it'll tell you all of the defaults. mtry is usually the square root of the number of variables that you have. And so an mtry of 4 is actually relatively high for our data set because we have only 4 variables. So we're trying all of the variables at the same time. If you have a more complex data set, this could become more important, okay? So, but I'm going to show you how we can tune the model and change those 2 parameters, okay? So I'm going to run set seed, and then I'm going to run rf. And notice we get an object called rf.mod. It's a list of 19 objects. There's a lot going on there. But we can plot this and have a look at the first little bit of insight into our data as fit through a random forest. Okay, so we can zoom in on this. And what this is showing is across these 500 trees that we've created, starting with just fitting a small number of trees and then going up to 500, you can imagine that as you grow out more trees, at some point you're going to saturate the variation that exists there, because there's only so many options or so many random combinations, especially with our limited data set, that can be created, okay? So that's the x-axis, that's across a gradient of trees. The y-axis is what's referred to as out-of-bag error. And so at the beginning, I told you that we grab a random subset of our data set, we put that into the bootstrap set or the bag, and then we replace it and we randomly draw another one. And then we do that. And as it turns out, only about 64% of your data are used to train the model. The rest of those that were in your original data set that weren't selected to go into the bag, those are the out-of-bag data. And so we can train the model with the in-bag data, and then we can basically assess how well it predicts the data that were left out of the bag. And this is the proportion of observations that were misclassified or erroneously classified. So 15%, 10%, 5%, 0%. Okay, everyone following our okay so far? And we're looking at that across a gradient of trees. And as you might expect, error is pretty high when there's a small number of trees, but then that comes down pretty quickly. And the lines that are shown here are each of the classes of species, and then the black line represents the average error across all of these. Okay, so Setosa was the one that we, in the classification tree, was perfectly classified every time. That one is just, if you remember all the way back to NMDS, that's the one that clustered way out on the axis in NMDS1, and then the other two showed some overlap. So we perfectly classify that one every time. The out-of-bag error rate is 0. That's amazing. You'll never see this with your own data unless you're using cleaner data than fish ecologists use. Most of the time, what you have is some high error rate that comes down, or maybe it goes down and then starts to go up as you grow out the trees. And then because we're only dealing with 4 variables here, this 500 trees, we don't see much after that, okay? So this black line is what you might focus on. This is the average misclassification or average out-of-bag error rate as the number of trees increases. And so what this is showing is, within approximately 50 trees, we had minimized the error rate, and then there wasn't much to be learned going beyond that. And if this was computationally expensive to do 500 trees, you might want to bring that number down. But in our case, that ran pretty quickly. It's a pretty simple data set with strong classification. Okay. I'm just looking at the, so could you use any number as the set seed? What's the downside of just using 1 as opposed to 187? Yeah, you can use any number there, Lindsay. And you could use the same number every time, but the idea is just to grab some stationary starting point that's based on randomization. So I don't know why I chose 187. On the next one, I chose 8675309 for any of those 80s music fans. It doesn't matter what the number is. It can be random, okay? But you just want to run that same number every time you run your model because you're going to get the same output if you run the same number, okay? Good question. So that's the first output. Then we can have a look at this object that we call randomforest.mod. And if I run that, and zoom in on this, wrong direction. Okay, now it tells us a bit of data about, or a bit of information about how the model performed, okay? So the call is a random forest model where we're predicting species as a function of all other variables in the iris data set. We're growing out 500 trees, and we're trying 4 variables at each split. The type of random forest is a classification. That's because we have a categorical response variable, and then it tells us kind of the same information here again. Here's our out-of-bag estimate of error rate. So if we looked at this average of the black line in the plot over here and converted that to a percentage, 4.67, that's pretty low error rate. And typically you want to see a very low error rate if your classifier is working. Then I'm just going to hit enter to get above this zoom window. Now what it shows is among observations that we know to be Setosa, how many were classified as Setosa, how many were classified as versicolor, and how many were classified as virginica. And notice all 50 of those were classified as Setosa. So 0 error. But when we go to versicolor, none of those were classified as Setosa. 47 that we know to be versicolor were classified as versicolor. That's pretty high. But 3 of those that we know to be versicolor were classified as virginica. So we have this 6% error rate. Okay, and then the same thing with virginica. I have a quick question.
I'm sorry to interrupt. This confusion matrix is perfect. So which is the one that is which columns or rather the columns or the rows are like what it was supposed to be versus what it ended up being?
Yeah, so the rows are what it's known to be.
Okay.
And then the columns are what are the classifications.
Thank you. Sorry, I missed that.
Yeah, it's an important point because I mean the confusion matrix does cause some confusion if you don't know which is which. But yeah, the idea is to just show misclassifications. And it's, you know, so here it's Setosa, but how is it classified? Okay. Everyone doing all right? Well, and I know I get these backwards sometimes. We're going to actually look at some other data in a minute that are more explicit in terms of those that were included as a species, but are another species versus the opposite of that. They're another, they weren't included. It's called omission and commission rate. Okay, so more on that in a minute, Alex. Okay. So that's the output from the model. Okay, there's much more to it, of course, but the other thing you can do. So if you use these, and we publish on these, and one of the criticisms that we often get is, well, how do you know how many variables to try? Because that's pretty important. As you might imagine, as you try more variables, the trees become more complex. So there is a function called TuneRF that is a part of the RF utilities package that we loaded. And all we do with TuneRF, so we have to use setseed again, but there's TuneRF. We tell it the prediction data set. So I'm just using indexing as we have all semester. Iris with the brackets, comma, everything after the comma is a column. I'm choosing with the concatenate function, columns 1 through 4. Then we tell it the response variable. And here I switch from indexing to just calling that single column that's known as species. I could have, instead of $species, put iris, then do the square brackets, then a comma, then concatenate, and then, or without concatenate, I could just put the number 5 in there, okay? Hopefully everyone's following this by now. And then there's a step factor, and that's where it increases the default number of variables that are tried. So the square root of your number of variables, it'll increase that and then have a look at across that gradient, what is your out of bag error rate, okay? So let me just show you. So I'm going to run set seed here on just a random number, but we'll use that same random number every time. And we get this output that looks like this, okay? So this is across, this is when one variable is tried. This is when two variables are tried. This is when three variables are tried. This is our out of bag error rate. And of course, we want to minimize the out of bag error rate, or the OOB error. And so notice 4 was selected. And so that gives you an idea of what to plug into the mtry there. Instead of just using the default, you can tune the model to use a particular number of mtry. Okay, so that's pretty straightforward. So sometimes this is iterative. You might change the step factor and go back and forth and see how it changes the number that should be added or tried at each split. Ours is not going to go higher than 4. You could increase that step factor all you want. It's never going to go past 4 on the x-axis here because we only have 4 predictor variables. And one of the benefits of these random forest models is that they can handle a large number of predictor variables relative to the number of response variables, okay? And so like if you wanted to do multiple regression, for example, it becomes pretty complex to throw everything into that model. And so what we find is that random forest models are typically used in hypothesis development. So run everything through the random forest model. What are the variables that shake out as most important? I'm going to show you how to do that next. And then you could go in to do maybe regression-based modeling on just those important variables. Okay, so it's a useful classifier for things like species distribution models, but it's also used for hypothesis development. Okay, so Alex, I'm just seeing your comment from earlier, but are you good? Okay, cool. So then what we can do is look at the importance of each of these variables. And so the function to do that is var, all lowercase, imp with the capital I, which is short for importance, and then plot, which is with a capital P, which means that we're going to create a plot. And because I had changed the infro here to 1 and 1, it's only given me one of the plots. We can go in and change this to 1 and 2. Nope. There we go. Let me try one more thing here, because nope, that's not one. I'll just explain to you the there's 2 options here. There's either mean decrease in Gini, which we use, or there's mean decrease in accuracy. But the preferred is to use this mean decrease in Gini, G-I-N-I. And this is a measure of earlier what I referred to as node purity. It is the node classifying down to just a single, in our case, a single species, and is that the only one that's in there? And so what this does is it looks across all of those 500 trees that we created, and it considers trees that exclude, by random, that exclude petal width. And it looks at relative to trees that do include it, those that exclude it, what's the change in node purity, or what's the mean decrease in Gini. Okay, so a big decrease in Gini would represent an important variable that's been left out of the model. And so we can use this mean decrease in Gini where a higher value actually represents a more important variable, okay? And notice that if we look at these, we've got petal width has the largest mean decrease in Gini, and then petal length is close to it. But then notice sepal width and sepal length are much smaller values. And the magnitude of your mean decrease will probably change depending on each model that you fit. It's not like it's scaled between 0 and 100 or something like that. It's totally dependent on the data set that you're using and what your kind of background node purity looks like, okay? The idea is not to use some value on this x-axis as a cutoff, but just to consider the relative importance of the variables, okay? And so we could conclude, well, petal width and petal length are both important. Petal width may perhaps a bit more important than petal length. And certainly those two, we would want to investigate these further over sepal width and sepal length, okay? So you can imagine this is much more useful when you have a huge number of predictor variables and you're trying to whittle that down to just those that are important for explaining variation in the classification in this case, okay? So one of the criticisms of these, they're sometimes referred to as black boxes. So we know that a classification is happening, but we don't always know how that classification is happening, because there's it's a machine learning process, and so we don't always have a glimpse into how these models are learning about the data. But one of the best ways of getting a glimpse into how these predictions are made is to think about what are the most important variables, and then what is the probability of assignment to particular classes across those variables if we hold all other variables at their average value. And that's a concept known as partial dependence. So for example, we're going to look at petal width, but we're going to hold petal length, sepal width, and sepal length at their average, and then consider what the classification probability looks like when we allow petal width to vary but nothing else, okay? In this rf.partial.prob is a function from the RF utilities package that we loaded earlier. All we have to tell it is our model. So x equals the model. We call that rf.mod. We just have to tell it the predictor or pred.data, which came from Iris. We just have to tell it the name of the individual predictor variable that we want to consider. So in this case, petal width. When we're dealing with 3 classifications like we are today, we have to tell it which class we're interested in. If you had a yes or no, you're usually like a 0 and a 1. You're usually interested in predicting the occurrence or the 1. But here we're gonna say what's the probability that a plant is classified as virginica across a gradient of petal width, okay? And then it'll add a smooth spline to it. And so I'll show you what this looks like, okay? So we're gonna run this and we get this output. Zoom in on this, okay? So now what we're looking at is petal width on the x-axis increasing across its original scale, and then we have probability of being classified as virginica on the y-axis here, where 1 would represent absolutely that is a virginica, and 0 would be absolutely that is not a virginica, and then values in between would represent some probability of being classified as yes or no for that species. And so what we can conclude from this is that when petal width is less than 1.5, the species is not classified as virginica. And then when petal width is greater than 1.75, we have pretty we have perfect classification of that species as virginica. And you can do this for each of the classes. You could, if you're interested in one particular species of Iris, or you could do it for each of the predictor variables if you're interested in knowing how those influence the classification. And so in my research, we typically think about presence or absence of fish species that are in need of conservation. And what we typically look at are things like land use cover. So this might be forest land use cover on the x-axis in our case. And what we typically see is in the naturally forested area, there might be a high probability of occurrence when forest coverage is high. But then as we start to transform forest land cover into urbanization or agriculture, what we typically see is a reduction. So sometimes you're interested in what does it mean from the predictor variable standpoint, or sometimes you're just interested in how do we collectively, across multiple predictor variables, classify a species. Okay, and the last thing that I'll show you then is this idea of cross-validation. And this is where, if you're confused by the confusion matrix, and sometimes I can't remember if I'm interpreting it in the correct way, rows versus columns, you can always do question mark random forest, and it'll explain to you in the help file what the rows versus the columns mean. But one of the best ways to think about how a model is performing, it's sometimes called model validation, sometimes called model assessment. There's some semantics there, but essentially what we're asking is, well, okay, if we hold back some of the data, even before the bootstrapping process, if we hold back some of the data, and we fit the model, the random forest model on a training subset of the data. We go through the whole process of the bootstrapping, get the bag and out of the bag, and then we go through creation of all of the random trees. And then we have our classifier, our random forest model. Then we can evaluate how that model is used on a totally independent data set that was never used in the training data set, or even on the table for being included in the bag. If you do that, if you subset your own data set, we call that cross-validation. And typically what you do is you hold back a small section, subset of the data for the training or for the test data set, and you use a larger fraction of the data for your training. So you train the model with the larger fraction of the data, and then you test it on a small fraction of the subset of the data that we call the test data set. And so in this package RF utilities, there is a function called rf.crossvalidation. You just tell it your model, you tell it your predictor data, you tell it the response variable, you can tell it the, so we can use the, I'm trying to remember what P, oh, the proportion of the data that's held back, the number of cross-validations that are done, and then notice seed is included in the function here. So we don't have to run set seed and then do the cross-validation. We can include the seed, and I randomly chose 597. You can choose any number you want as long as you use that same number every time. You should get the same output from your cross-validation, okay? And if you have a really big data subset, you might be able to hold back a greater proportion of the data and do a greater number of cross-validations. As your data set becomes smaller and limited, you can't hold back, you might not be able to hold back as much of it, and you may not be able to do as many cross-validations. And so this is just returning to this idea that I mentioned at the beginning, that these are pretty data-hungry models, meaning that you gotta have a lot of observations to run these things. Okay, so we can run this cross-validation, and it says running it, it's using 900, or it was doing 99 iterations, so it takes a little while to do it. So it does the cross-validation. So you get classification accuracy from the cross-validation, and then classification accuracy from the model. So cross-validation is where you're using a subset of the data, going through the whole process, and then using the model on that subset of the data. And then classification accuracy from the model is just considering the out of bag versus in bag, okay? So if you do a cross-validation, you want to report the results from the cross-validation, the first chunk of data, okay? And then it gives you the user's accuracy and producer's accuracy. And I've given you a little note here. So user's accuracy, also known as error of commission, also known as inclusion, also known as false positives. So that's the first, what fraction of the data for Setosa were false. Well, so this is accuracy, which is just 1 minus error, okay? So this is if you did 1 minus the other, so user's accuracy would be 100% of those that we know to be Setosa were classified as Setosa. Same thing with Erica and Virginica. The second, producer's accuracy, also known as error of omission, also known as exclusion, also known as false negative, there's essentially 0 there. So in our cross-validation, because this model performs so remarkably well, when we cross-validate it, it's a perfect predictor. You'll rarely see that with your own data. There's a reason that the example data sets are chosen as the example data sets, because the models usually perform well on those data. And then you can see when we go back to classification of the model, when we consider in-bag versus out-of-bag, we're not quite as perfect there. But by using the cross-validation, we actually find that the model performs pretty well. And the whole idea here is we're getting a sense of what's sometimes referred to as overfitting. So creating a model that is so complex and nuanced that it really explains your training data very well, but when you bring in new data and you fit that model to new data, the model might perform poorly if it's overfit. And so doing this subset or cross-validation gives us an idea of how the model might perform on new data, and therefore the degree to which it might be overfit. And one of the benefits of regression trees or random forest trees is that because we're using random subsets of the data across so many different trees, they tend to be pretty robust towards this issue of overfitting. But depending on the nature of your data set, you could still overfit the model, particularly if you have a small data set. So cross-validation is a way of getting a handle on that. The last thing that you might do if you fit a random forest model is go through this validation process on a totally independent data set. So for my research, when we do this on fish distributions, we might use a data set collected by one entity, train our models, do our cross-validation, assess how well the model does, and then we may go out and request data from an entirely different entity that is independent of the training data set entity, and then we do another validation or assessment of the model on new data, like totally new data or independent data. That would be the only other thing that you might want to report on a random forest model beyond this cross-validation. Okay, there's a crash course on random forest. There's a lot of nuances there that I'm happy to talk about with each of you if you decide you want to do random forest stuff. We might have 1 or 2 people presenting in this class on random forest, so you'll see some of this stuff again. Any discussion before I end the recording on random forest? As I said earlier before we started recording, no expectation of a coding assignment here. This is the last lecture of the semester. I think we're all just kind of ready to be done. But any discussion? I think we're caught up on the chat. Okay, all right, I'm going to stop the sharing or recording.